So come across the BSc 4th semester subject mathematics, the modular infinite sequence, the class number, or you can say session number 5. In this class I am going to derive the Cauchys second theorem on limit of a sequence. As per this regarding the syllabus oriented from the Karnataka University Dharwad. So I move towards the statement and proof of the Cauchys second theorem on limit of sequence. Here it is the theorem. Theorem 5.2, 5.1 has been considered the Cauchys first theorem. There we derived that if the sequence an converges to L, then the arithmetic mean of the an also converges to L. Look at the Cauchys second theorem. If an is a sequence of positive terms, then limit n tends to infinity an to the power 1 by n is equal to limit n tends to infinity an plus 1 divided by an, provided the limit on the right side exists finitely or infinitely. So what it is given, and we have to be proved in this theorem. An is a sequence of positive terms. It is clear idea. Then one expression has been given in the equal symbol, that limit n tends to infinity an to the power 1 by n is equal to the limit n tends to infinity an plus 1 divided by an, provided the limit on the right side exists finitely or infinitely. It means that to consider the right side limit, that limit n tends to infinity an plus 1 divided by an, if it is finite, then the left side expression is also finite. If the right side expression is infinite, then the left side expression is also infinite. You have to be show or prove this thing in the theorem. So let us consider the proof. I will take, let limit n tends to infinity, the right side expression an plus 1 divided by an is equal to L. What does this L? There are two cases of L, either L finite or infinite. Now to consider the case 1, that L is finite. What it is? L is finite, limit n tends to infinity an plus 1 by n is equal to L. Apply the definition of a limit for a given epsilon greater than 0, however small, there exists a natural number m such that the symbolic definition has been converted into the modulus by means of definition, such that modulus of an plus 1 minus L is less than epsilon by 2 for every n greater than or equal to m. Now I have to take the advantage of this modulus. If it is, suppose for example, mod x is less than 1, it means that x is in between. Mod x is less than 1 means x is in between 1 and minus 1. Suppose if the expression modulus of this is less than epsilon by 2 means this thing an plus 1 divided by an is in between L minus epsilon and L plus epsilon. That I written in the next step, that an plus 1 divided by n is less than L plus epsilon and greater than L minus epsilon by 2. At that I return L minus epsilon by 2 less than an plus 1 divided by an, it is less than L plus epsilon by 2. Keep in mind that for every n greater than or equal to m. So you may call this has to be 1 or no. Okay, then for every n greater than or equal to m means I will take the value of n from m and greater than m. I will take in this expression I will put the value of n from m and thereafter increasing m because n greater than or equal to m. So whenever I put n equal to m here, no changes in L minus epsilon by 2 and L plus epsilon by 2, only changes where it is n changes to m. So this is L minus epsilon by 2 less than am plus 1 divided by am is less than L plus epsilon by 2. Next in this expression I will put n equal to m plus 1. When n equal to m plus 1 has been taken, again no changes on the left side inequality L minus epsilon by 2 and right side inequality L plus epsilon by 2. The n becomes a m plus 1, n becomes a m plus 1. So this is m plus 1 becomes m plus 2. The denominator n becomes a m plus 1, a m plus 1. Like that this process goes on to be continuing to put n equal to n minus 1 here. And that time the left and right side inequality remains same. Put n equal to n minus 1. This is becomes a n minus 1. There were already plus 1 and that minus 1 cancels. We left a an. The denominator becomes a an minus 1. Now our idea is to that you have to multiply all these inequalities, multiplying. If how many inequalities are there? You are starting from n equal to m and ending n minus 1. Starting from n equal to m means you left the m inequalities already. You left, you are not taken. That means these are n minus m inequalities. Multiply above n minus m inequalities, n minus m equalities, we get there is L minus epsilon by 2, L minus epsilon by 2 multiplied L minus epsilon by 2 by n minus m times. It becomes no doubt that L minus epsilon by 2 raised to n minus m. And right side also same, L plus epsilon by 2 raised to n minus m. Whenever multiplying these fractions, am plus 1 divided by am into am plus 2 divided by am plus 1, that means the numerator of the first fraction is cancelled with the denominator of the second fraction. The process goes on to be continuing. Look at the last term, an divided by an minus 1. Its previous numerator cancelled with the denominator of the last term. That means we left am in the first inequality of fraction and an in the last. That means denominator side, whenever we are multiplying all these, numerator we have a an, denominator we have a am. So this expression becomes, after the multiplication, L minus epsilon by 2 power n minus m is less than an by am is less than L plus epsilon by 2. Now the denominator has been avoided am by means of multiplying throughout by am. Whenever multiplying by am, the am becomes to the left side inequality, to the right side inequality, we left an in the middle. So what happens whenever multiplying am? So this is am into L minus epsilon by 2 to the power n minus m is less than an is less than L plus epsilon by 2 to the power n minus m into am. Now our idea is to take power 1 by n for every expression, raising power 1 by n. Whenever I am raising power 1 by n, am is am to the power 1 by n. Now L minus epsilon by 2 to the power, already there is a n minus m. I am raised 1 by n means that 1 by n is multiple to the n minus m, or it means that n minus n is divided by n. Similarly, an to the power 1 by n becomes, and it is L minus epsilon by 2 into to the power n minus m by n into am to the power 1 by n. Now our idea is that apply limit n tends to infinity to this expression. Same thing with return, left side of inequality I applied limit n tends to infinity, middle limit n tends to infinity, an to the 1 by n is applied, and here it is also I am applied. Now I will consider what may becomes limit n tends to infinity of this an to the power 1 by n and L minus epsilon by 2 to the power 1 minus m by n. I hope it is clear. N minus m by m, split the denominator to the both numerator, n by n is 1, m by n I left. Same thing is here. Now I will consider the limit n tends to infinity am to the power 1 by n into L minus epsilon by 2 to the power 1 minus m by n. When n becomes a infinity, the first term that is am to the power 1 by n is infinity, 1 by infinity. The power becomes a 1 by am to the power 1 by infinity is nothing but the am to the power 0. That means 1. And again L minus epsilon by 2 same, again denominator n becomes a infinity, the m by n becomes 0. We left L minus epsilon by 2. So the left side of inequality, when I applied n tends to infinity, it becomes a L minus epsilon by 2. For every n greater than or equal to m1 I can take for the new limit. Okay, now the right side inequality, the same thing happens. It L plus epsilon by 2 when n tends to infinity, it becomes a 1. There is L plus epsilon 2, the new integer n is greater than or equal to m2 I can take it. Now the expression 1 becomes, the left side inequality is L minus epsilon by 2, The right side inequality is L plus epsilon by 2. Therefore, it is L minus epsilon by 2. Limit n tends to infinity an to the 1 power 1 by n is less than L plus epsilon by 2. Now, to take the n greater than or equal to m, this m is the maximum of m1 and m2. What does it mean by an to the power 1 by n is in between L minus epsilon by 2 and L plus epsilon by 2? That is nothing but the modulus of an to the power 1 by n minus L is less than epsilon by 2 for every n greater than or equal to m. So, this is the meaning of limit n tends to infinity an to the power 1 by n is equal to L. So, we taken the right side expression L is to be finite, that is limit n tends to infinity an plus 1 divided by an equal to L. I can take an finite. The limit n tends to infinity an to the power 1 by n left side also becomes a L. So, this completes the first case of the proof. Let us move towards the second case, case 2. Let L is infinite. When L is infinite, to take the right side of the given expression limit n tends to infinity an plus 1 by an equal to infinity. I will make the terms reciprocal of numerator, reciprocal of denominator, and immediately the result is also reciprocal. Now it is limit n tends to infinity, reciprocal of an plus n is 1 by an plus 1, an is 1 by an, infinity is 1 by infinity, but in 1 by infinity value is 0. So this expression becomes limit n tends to infinity, 1 divided by an plus 1 divided by 1 by an becomes a 0. It is finite. We already did the theorem in the case of finite. If it is a finite means immediately the limit n tends to infinity, the 1 by an to the power 1 by n is also becomes 0. It is by case 1. So, limit n tends to infinity by case 1, it is limit n tends to infinity 1 divided by an to the power 1 by n also becomes a 0. Again convert it into the reciprocals. 1 by an I changed as a an. And 0 is immediately changed as a 1 by 0, that is infinity. So, we get that limit n tends to infinity, an to the power 1 by n also becomes a infinity. So, we can taken that, initially we can taken that right side of the limit either finite, then immediately left side is also finite. If the right side is infinite, immediately the left side is also infinite. In this way, we approach the second Cauchy's second theorem on limit of a sequence in a very smooth way. I hope it is clearly understand to all of you. If any queries, any doubts, you may put the questions on the YouTube channel or my to WhatsApp number or to my mail address. Nothing, no problem at all. I will give the answer for those doubts. So, this complete the second theorem of Cauchy's theorem on limits. Thank you, one and